I welcome all of you to the class. As far as today's class is concerned, today we'll be discussing about the one more method of finding the slope and deflection of the beams. And today's method is known as the method of virtual work or the virtual work method. As far as the virtual work method is concerned, how does a virtual work method work? To find two things. One is virtual work method is used to find the slope, and second is it's used to find the deflection, slope and deflection of a beam. We will write of a loaded beam, okay? Of a loaded beam. What does that mean? That means that we load a beam, we apply load on the beam, and as far as the beam is concerned, the beam deflects. Okay, if you look at the beam that is given to us, this is a cantilever beam, and this cantilever beam is subjected to a triangularly distributed load. Okay, so under the application of this triangularly distributed load, this entire beam will bend, and its bending curve will be like this. Okay, this is how the beam bends, and we have already discussed while we were talking about the deflection of the beams. So the distance from originally the beam was, before the application of the load, the axis of the beam was straight, but under the action of the load, the beam has taken a curved shape. Okay, so initially the point was here, now it has moved to this position, and this is what we call as the deflection. Okay, this is called deflection. And if we happen to draw a tangent, if we draw a tangent to any point of the this curved portion, this curved trajectory, what you call as, if you draw a tangent, for example, draw a tangent here. Okay, the angle that the tangent subtends, the angle that this tangent subtends with the ground, this angle, let's call this as theta. This is what we call as, this is called slope. Okay, so this is what we call as the slope. This is slope, and this is what you call as the deflection. Okay, so as far as today's topic is concerned, in today's topic we have to talk about the slope and deflection. Okay, we have to find the slope and deflection of a beam using the virtual work method. Okay, the concept is that we have been discussing about the method of finding the slope and deflection of the beam, and we have used many methods, like we have used the double integration method, we have used the Clapeyron's three moment equation method, and there are many other methods available for finding the slope and deflection of the beam. And this method is one among them. The virtual work method is one among the methods for finding the slope and deflection of the beams. Now the question is, how does the virtual work method work? Now, in order to make you understand how does the virtual work method work, it's very easy. We can easily solve it. We can easily work with the virtual work method. We can easily understand how this method works. In order to make you understand what I am doing, let's take up a cantilever beam, and the length of the cantilever beam is, say for example, L. Okay, let's suppose the length of this cantilever beam is, L. Okay, this cantilever beam is subjected to a triangularly distributed load having zero intensity at x is equal to 0. This is one end of the beam, and having some intensity. Let's call this value of the intensity as, let's say the value of the intensity of the load is here W, and this is at x is equal to L. Okay, so the total span of the beam, or the total length of the beam, is L. Okay, so the total length of the beam is L. Okay, so and x is equal to 0, the beam is having no load at all, but at x is equal to L, the intensity of the load is W. Okay, so how do we find out, how do we apply the virtual work method to find the slope and deflection? The question is, let me write down the question here. What the question says, question is, find the slope and deflection, find the slope and deflection, find the slope and deflection of the cantilever beam with triangular distributed load, find the slope and deflection of the cantilever beam with triangular distributed load at its free end. Okay, let's suppose we have to calculate the value of the question says that we have to calculate the slope and deflection at the free end. Okay, that is at x is equal to 0. X is equal to 0. Let me call this as A. Let me call this as point B. Okay, so we have to find the slope and deflection at point A. So now what we do, we have to use the method that we have to use is the virtual work method. In order to work with the virtual work method, first of all, what we have to do, the first and foremost step is, in the given beam, calculate the bending moment equation. Okay, write down the bending moment equation for the given beam. And we know, in order to write the bending moment equation, what we do, we will first of all draw a section. Okay, let's draw a section of the beam, and let's suppose we draw a section over here. Let's take a section of the beam here, such that the distance from x is equal to 0 to this position is x. Okay, so once we have taken a section out, okay, the section that will come out, this section, once we take out, this section will be, it will be like this. So this is x, and it is subjected to the triangularly distributed load, and the distribution of load is like this. Okay, so the distribution of load is like this, and overall it is subjected to it is having triangularly distributed load over it. Okay, we know this thing, and it is triangularly distributed load all over it. Okay, so now what we do, let's do the analysis. The portion where we have this total distance is x. Okay, and the portion where we have taken the section, let's say our shear force is V, and let's suppose our bending moment is M. Okay, this is our bending moment. Okay, now this is the intensity of the load at x is equal to L is W, and the load varies. If you look at this small triangle, this triangle, and the larger triangle, and the bigger right angle triangle, both the two triangles are the right angle triangles, and both are similar triangles. Let's suppose the intensity of the load here, or the intensity of the load here, is W1. Okay, therefore by the concept of similar triangles, we can write W by W1. W by W1 becomes equal to, W is a part of the bigger triangle, that will be equal to L, that is base, and divided by the base of the smaller triangle, that is x. Okay, which implies, as far as W1 is concerned, W1 becomes equal to W by L multiplied by x. Okay, so this is W1. As far as the intensity of the load here is concerned, that's equal to W by L into x. Now I have the first step which I told you is to find the moment equation, that is M. In order to find the moment equation, what I do, let's start taking the moment of all the forces about this point. Okay, as we start taking the moment of all the forces about this point, first of all we are having this moment M, and this moment is anti-clockwise, this is M, and there will be the moment because of this triangularly distributed force, whose intensity will be, first of all, its magnitude will be half of base, that is x, multiplied by the perpendicular is W1. W1 is equal to W by L into x, so it is W by L into x. Okay, so this is the magnitude of the force. Okay, this is to be multiplied by the force arm. We know that triangular distributed load will act where? This triangularly distributed load will act at the centroid. Okay, and as far as the centroid is concerned, the distance of the centroid from the perpendicular end, from the 90-degree end, is, from this end, is x by 3. Okay, therefore we are taking moments from this point, therefore the force arm of this force will be x by 3. Okay, this is x by 3. And what is this moment now trying to do? If you look at this moment, it's trying to rotate this portion in the anti-clockwise direction. Therefore, this has to be positive, and this is equal to 0. Okay, we can write this as, therefore, the bending moment equation for the beam becomes, M becomes equal to W x cube divided by 6 times L, but minus. Okay, so this is the bending moment equation, Wx cube by 6L. This is the bending moment equation for this cantilever beam. Okay, now once you have performed this analysis, once you have obtain the bending moment equation. The first and foremost step is to obtain the bending moment equation that we have obtained. Now, once you have obtained the bending moment equation, redraw your beam. I mean to say, redraw your beam in such a way such that you remove all the loads acting on your cantilever beam. Okay, remove all the loads acting on the cantilever beam. This is important. Okay, remove all the loads acting on the cantilever beam. We have to find the slope and deflection at point A. Okay, so in order to find, first we will be finding the slope. Okay, so first we are actually finding the slope. Okay, so we are finding the slope. This is the procedure for finding the slope of the beam. We have to find the slope of the beam at point A. Now remove all the loads from the beam. Okay, where we have to find the slope, we have to find the slope at point A. The point where you have to find the slope, apply a moment in clockwise or anti-clockwise direction. This is your choice. Apply a moment of 1 unit. Okay, so what we have to do, I'm repeating, in virtual work method, wherever you have to find the slope, the point where you have to find the slope, the point where you have to find the slope, at that very point, apply a bending moment equal to 1 unit. Okay, equal to 1 unit. Fine. Now, once you have done it, okay, once you have removed all the loads from the beam, we have to find the slope of the beam at point A. What we are doing, we are removing all the loads. And at the point where we have to find the slope, what we are doing, we are actually, we are drawing, we are assuming a moment of 1 unit, clockwise or anti-clockwise. This is your choice. Let's assume the moment is being applied clockwise, and you have to take the magnitude of the moment we have to apply is equal to 1 unit. Okay, once you have done this, now do the analysis again. That is, I mean to say, now obtain the bending moment equation for this beam. Okay, now how do you obtain the bending moment equation for the beam? In the same way as we obtain this. Okay, draw a section at any point. Once you are drawing a section, let's suppose that this distance from the point O, this is equal to x. So, okay, at this point, let's suppose remove this portion of the beam. So as we remove this portion of the beam, so this is the portion of the beam that we have, and at one end of the beam we are having a moment of 1 unit acting, which we have applied virtually, and here this distance is x. Okay, this distance is x, and at this end where we are taking the shear force, let the shear force be V, and let's suppose the value of the bending moment is, say for example, m. Okay, now obtain the value of this m. So we will make a difference between this m and this m. This m we write as mr. This is the real bending moment, actual bending moment. Okay, and as far as this bending moment is, this bending moment is the bending moment in the beam when we are assuming no load acting on the beam, but simply a moment at its free end. Therefore, this is not the actual bending moment. This is called the virtual bending moment. We write this as V subscript V. Okay, obtain this V. Take moments about an axis passing through this point where you have taken the section. So first of all, you have this anti-clockwise moment. This will be m virtual, mv, and there will be the moment. This is 1 unit moment, and this 1 unit moment is clockwise. Therefore, we'll be taking this as minus 1 unit of moment. There is no other force, no other moment. Put that equal to 0. Therefore, the virtual moment becomes equal to. Therefore, the virtual moment becomes equal to 1 unit. Okay. Now we are having, call this as equation 2. Okay, we're having 2 equations. Fine. We are having the real moment equation, and we are having the virtual moment equation. Okay, now as far as the principle of virtual work method is concerned, the principle of virtual work, the 1 unit of load, what now, so we have obtained virtual moment, we have obtained the real moment. Then the principle of virtual work states, okay, by the principle of virtual work, the deflection at point A, where you have applied this unit moment, okay, the deflection, sorry, the slope at point B, the slope, since we are trying to find the slope at point A, not point B, the slope at point A, the slope at point A is equal to integral from 0 to L, integral from 0 to L, okay, integral from 0 to L, real moment of the beam multiplied by the virtual moment of the beam divided by flexural rigidity, that is E into I dx. This is, I will explain it later on. This is called this is from the principle of virtual work. That is, the principle of virtual work says that slope at point A. The slope at point A is equal to integral from 0 to L real moment multiplied by the virtual bending moment divided by EI multiplied by the that is integral over dx, because this is our x-axis. Okay, that is deflection at A, sorry, slope at A becomes equal to integral from 0 to L mr, the real bending moment is minus w x cube by 6L. We'll write this as w x cube divided by 6 times L, but this is minus, we'll take this minus out. Okay, multiplied by a real moment is 1, and you have your EI, that is EI, and this is dx. Okay, therefore it becomes w is constant, it will come out, 6 is L, EI, they are all constant, so it will become minus w by minus w divided by 6 LEI, and we have integral x cube dx is x raised power 4 divided by 4. The value of integral goes from 0 to L. This becomes, okay, this becomes minus w L raised power 4 divided by 6 cross 4 is 24 divided by 24 EI. WL raised power 4 divided by 24, and you are having this L at the bottom, this L we're having in the denominator L. Okay, this L and 1L will cancel, it will be L cube. That is, from here we will obtain the value of the slope at point A is equal to minus W L cube divided by 24 times EI. Okay, this is the value of slope of the beam at point A. This is by what method? This is by the method of virtual work. Okay, this is how we have to find it. So the question is, if we have to find the slope, the question was that we have to find the slope at point A. In order to find the slope at point A, wherever you have, maybe you have to find slope here at point C. Wherever you have to find the slope, assume a bending moment of 1 unit, clockwise or anti-clockwise there. Okay, so first of all, find the real bending moment and multiply the real, after finding the real bending moment, find out the virtual bending moment. Virtual bending moment means that what you have to do, you have to find the bending moment in the beam. Wherever you have to find the slope, at that point you have to apply the unit moment, clockwise or anti-clockwise. Then use this formula or this principle of virtual work to find the value of the slope at that very point. So this is about the slope. Now we have found the slope. Now we have to find the deflection. In order to find the deflection, let's go to the next class. Now, in order to find the deflection of the beam, what we do, let me rub it up. In order to find the deflection of the beam, what the equations that I have to use are already present there, except for one thing, that in spite of using a triangularly, you have to replace something. That is, now what we will do, we will redraw our beam. Okay, we will draw our beam. This is our beam. Now, on this beam, okay, what load is actually applying? The load that is actually being applied on the load is on this beam is a triangularly distributed load. Okay, this is x is equal to 0. This is our x is equal L. This is our point A, and this is our point B. Okay, so now what we will do, we have to find, we will remove all the load from the beam in order to find the deflection. Now point 2 is we have to find the deflection. Finding deflection is now easy. Okay, because what we did for finding the moment, same we will do for finding the deflection. That is, we have to find the deflection at point A. The point where you have to find the deflection, be careful, the point where you have to find the deflection, at that point apply a unit load. At that point apply a unit load. I will apply a unit force here. Okay, If my entire force is given in kilonewtons, then this is 1 kilonewton. If my force is given in newtons, then this is 1 newton. Okay, so the point where you have to find the deflection, at that point apply a force of 1 newton. Once we applied the force of 1 newton, what we will do, we will simply, after applying a force of 1 newton, what we will do, we'll simply apply the, we have to find then the equation of, we have to find the bending moment equation. How do we? Now after applying a unit force at the point where we have to find the deflection, apply the unit force, apply the unit force, okay, and now find the bending moment, okay. Cut the beam out. As you will cut the beam out, the section that will come out will be like this, okay. And we'll say that we'll say here we are having a force of 1 unit acting. At this point we are having a force of 1 unit acting. This total distance is x, okay. Here we suppose the shear force is V and the bending moment is M, okay. We have to find this bending moment for this case. Now take moments about an axis passing through this very point. So we are having this anti-clockwise moment. We'll call this as M, okay. I will again call this as M virtual, okay. We'll call this as M virtual 2 because we already had one virtual moment, because of a unit moment at point A, okay. And we have the moment because of this 1 unit force will be anti-clockwise. So this is plus 1 into x, that is x has to be equal to 0. Therefore the virtual moment 2 becomes equal to minus x, okay. So we have found the moment after applying the unit force. Again, now the virtual work method formula says the value of deflection at point A is equal to integral going from 0 to L. The real moment multiplied by the virtual moment, in this case that is mv2, divided by 6 LEI, okay. And this is to be integrated with respect to x, so this is dx, okay. That becomes equal to, as far as the real moment is concerned, that is minus, so minus will be out, w x cube by 6 times L, w x cube by 6L, and we have the virtual moment 2, that is minus x minus we have taken here, minus x by, and we are having here EI dx, integral going from 0 to L. That becomes equal, therefore deflection at point A becomes equal, W is constant, that will come out, 6 EIL is constant, they will also come out, the 6 LEI is a constant, that will also come out, 6 LEI. Then we'll be integral 0 to L, x raised power x cube into x, that is x raised power 4 dx, okay. That is x raised to power 4 dx, which becomes equal to W by 6 times EI L. This is integral x raised power 4 is x raised power 5 by 5, so that is L raised power 5 by 5, okay. So that becomes equal to, that is minus, okay. That becomes equal to, I will write here, therefore deflection at point A becomes equal to minus W L raised to power 4 divided by 30 times EI. This is the expression, okay. WL raised power 4 divided, mine says, as far as the mines is concerned, it means that the deflection is in the downward direction, mines, okay, because exactly the beam will bend like this, okay. Here it will be in the downward direction, that's what the mine says. So this is the deflection at point A, and we have already found the slope at point A. So this is how we have to find the slope and the deflection of the beam using the virtual work method. Let me give one problem as an exercise to the students. Let's suppose that we have a simply supported beam. We have simply supported beam at end A and at end B, And this simply supported beam is subjected to a uniformly distributed load. Let's suppose it is subjected to a uniformly distributed load. It is subjected to UDL. Okay. Suppose this beam is subjected to a uniformly distributed load. Okay, this is subjected to uniformly distributed load. And the intensity of this load is, say, for example, W. Okay, it's uniform. This length of the beam is, say, for example, L. Okay, the question is, we go to the center of the beam, point C. So using the unit load method, find the slope at point C and find the slope at point C, as well as find the deflection at point C using the virtual work method. This I am giving as an exercise to the students. This very easy method for finding the slope and deflection. We'll continue with more classes, hopefully next time. Thank you very much.